Hey, welcome to part 2 of my video series on training a reinforcement learning agent to play the game of Connect 4. If you haven't watched the first video yet, make sure to do that. I will link that in the description below. But in that video, we built the Connect 4 game from scratch using pygame and Python, and we kind of discussed the logics and the game mechanics, but we also train a very simple reinforcement learning bot to play against a random opponent. In this episode, we're going to do a bit of tuning on the model. We're going to have a few adjustments made. Most notably, we're going to be adding experience replay, double DQN networks, and making other small training adjustments to the model. So let's get started. The first adjustment we're going to make is called experience replay. Experience replay is a method used for stabilizing the learning that occurs in RL agents. So in our base implementation, we train the neural network value function after every move of the board, which can present issues. Most notably, training is unstable using this form of online training, especially with batch sizes of 1. And what I mean by online training is the model parameters are updated while the game is being played. In essence, our model is being too sensitive in reaction to singular moves, and we'd like our model to learn from a larger number of samples to help smoothen this effect. Our models can also forget what it learns as a result of placing too much emphasis into a single instance or move. To build intuition for this, let's take an example of an RL bot learning to play the game of chess. Let's say that the bot makes a move bishop to b4, which results in a win in a past game. In a future game where a similar but maybe slightly different state situation presents itself, the agent might make the same move bishop to b4, but this time it ends in a loss. And as a result, an agent that takes only the last move in consideration would get really confused at this because bishop to b4 should have been a good move, and that's why we made it in the first place. So it updates its value estimation to be of much lower value for this move because of what it just experienced. This then would lead to oscillations in its understanding of these moves, which in short should make the agent somewhat short-sighted in its understanding of the task that we're trying to teach. To remedy this, we store memory to generate larger batches for training to smoothen out our parameter updates. We are basically storing samples of experiences from the past into a queue, and from that we'll sample a certain number of those experiences and then average those values out to do our parameter updates for our neural network. Incorporating memory also enables reusability of past experience to continue training the model. This is almost like reviewing your notes or textbooks after a lecture in school. Experience replay has the benefit of enabling the model to learn new things about the same experiences. When we reread our notes from a past lecture in school, sometimes the simple repetition can allow us to see things in a new light and then make connections about the subject matter. In the time that we spend away from some subject, we could have picked up other learnings that can help us kind of connect the dots when we do revisit past materials or notes that may have been confusing before. An RL agent that learns from a set of experiences and moves on to future experiences to update their parameters and their understanding of the task at hand can then come back to past experiences to learn new things about them. This is a graph of the RL bot setup before and after experience replay. In the initial implementation, we have the state, which is contained or provided by the environment in gray. And this state is fed into the RL bot, which contains our neural network value function. Based on the Q values that this value function produces, we then select some action, which we feed back into the environment. This action then leads to a reward that our agent receives and a new state, which eventually becomes the next state to feed into the model. This reward, as well as the action, are fed into this training loop, let's say, where we update the parameters with a batch size equal to 1 and update our neural network. Now, on the other hand, with experience replay, we have a similar loop where we feed the state into the value function and then produce an action. But before entering this training loop, we actually feed the action, the reward, and the next state, as well as the current state, into this memory batch, let's say of size 1000 past experiences, and then this memory batch is sampled into the training loop where we take, let's say, 200 of those 1000 experiences, and we average the values and then calculate our new Q values for the updates to the value function neural network. And the batch size 200 and the memory size 1000 is inevitably a hyperparameter that we'll be tuning in future episodes to experiment with what works best for our given task. So this is the snapshot view into the RL bot class. In our initiation of the bot, we will create a memory, which is just a DEC or a DQ class in Python. And we specify the maximum length, which is 1000 past experiences. And how this works is when you append to this DEC, it will automatically remove the oldest values from the list of 1000. So if you already have 1000 items in this DEC or this list, and you try to append one more thing to it, it will actually automatically remove the first item that you put so that the maximum length of the DEC remains at 1000. So this is a nice, easy way for us to ensure that the memory size stays stagnant. And then we also initiate a batch size of 200 to be sampled from the memory. In the training loop, we will do our normal process, get the new state, get the reward, but here we store our experience. So we first gather the experience, and this is just a tuple of the state that we were in, the action we took, the reward, and then the new state after we took the action, but also an additional flag to indicate if the game ended as a result of that last move we made. And as a reminder, our result that we get from the environment is none when the game is still going, but it is not none, or a string denoting which side has won or drawn, if the result of the game is done. So here we append to that DEC list, and we store that in our memory. And if the length of the memory is less than our required batch size of 200, then we just return the function, return nothing, and we don't update any parameters. But otherwise, we can continue with the training loop. Here we're building the mini batch, we call them. So we're basically just random sampling from our memory based on the batch size, and we're taking 200 out of the 1000 items in memory. And then we are splitting out each of the state, action, reward, state 2, and done flags into different tensors. So this is going to be used for our model updates. We generate the Q values for the state batch, and then we also generate the Q values for the state 2 batch, and this is going to be our target value basically. And here we calculate again the reward plus the self.gamma times the maximum Q value. If the game was done, then that means that we actually zero this out. So all we receive is the reward batch because there is no new state to grab the Q values from. And then we calculate our X value as follows based on the Q1 values, and we'll do our normal backpropagation, loss update steps, optimizer steps, etc. To tackle the instability of learning in our bot, we also employ a double deep Q network or a DDQN setup. On a conceptual level, every state of the environment should be associated to some static value, assuming that we know what the true value is for each state. With online training, or training while playing the game instead of just after some number of games, every training and update iteration causes our estimates of the state values to change since we're constantly updating our model's parameters, and effectively this becomes a moving target for our model. Consider the original Q-learning equation below, where the Q value of the current state and the action is equal to the reward that we would get from taking that action in the current state, plus some gamma multiplied by the maximum value of the next action to take in the next state. When we update our estimate of the current state's value, QSA, by incorporating the predicted next state value, max QS prime A prime, we are essentially learning estimates using other estimates, because this in itself is an estimate. If we're using the same neural network value function to provide both of these estimates, this entanglement creates a constantly moving target for the model to learn, and this gives rise to instability. there needs to be a smoothing effect similar to the experience replay because significant learnings don't happen from single instances. They happen over several games and incrementally over time. And to remedy this, DDQN networks use a separate target network to estimate the value of the next state and action pair, so this side of the equation. This target network starts as an exact copy of the original neural network value function, but it doesn't update itself during every training iteration like the value network does. Instead, it stays static or doesn't update its parameters for some defined number of time steps n. This is again a hyperparameter that we can experiment with. After some number of time steps, the target network's parameters are synced with the value networks to kind of bring it up to speed with the current state value estimates. Basically speaking, the target network is just a lagging version of the original value network. So again, let's try to build some intuition around this. Imagine you're trying to improve at chess. Employing a learning strategy like DDQN could mean that you do the following to improve your skills. First, you'll play several matches, maybe 10, maybe 50, or maybe even more. Then you'll review all your matches together to distill and consolidate key learnings from the match, asking yourself questions like, what are key things that you're doing wrong? What are you doing right? Because you have several matches to learn from, you'll be able to see these patterns more clearly to really identify if certain things you're doing are in fact correct or incorrect. If you were to base it off of only one game, it's really difficult to tell if those things that you were doing wrong supposedly are really what you're doing wrong on the grand scale, or maybe there was just some kind of tricky situation or noise in that last game that you just played. Next, we'll update our strategy by noting down the specific things you need to work on moving forward. And this is similar to us updating the parameters of our neural network. Then we'll play more games and just simply repeat the cycle. A non-DDQN strategy might involve you analyzing games right after each one and then changing your strategy after every game based on your findings. And intuitively, again, this learning would be quite sporadic and chaotic because you'd never really know if the mistakes you made or the good moves you made in the last game were just simply due to noise or if they are actually genuine patterns in your level of play. Implementing a DDQN is actually very straightforward. Only a few lines of code need to be added. So here again is a snapshot into our RL bots where we instantiate a DDQN bot that inherits from our original RL bot class. The only thing we're changing here is the train function, just like before in experience replay. And in the initialization, we are initializing a few parameters here. The target sync frequency is 200, which determines how often we sync the target network to the value network. Basically, our target network, or this new DDQN network, will lag behind 200 moves behind the original value network. The target model itself will just be a deep copy of our existing model. And then here we make sure to just load the parameters of the existing model into the new target model. In the train function, we will do the normal steps, get the new state array, get the reward, store the experience in memory, and then sample the mini batch from memory for training. This is our experience replay that we just discussed. And then here we get the Q values for the current state using our original value network. So we use self.model and we call it on the state batch. And then here we're getting the Q values of the new states. So this right-hand side of the equation, we get the Q values of the new states using our target model. So this is the new model that we instantiated up here. And everything else is pretty much identical. The only difference is this line change where we use the target model to determine the Q values for the new states. And then lastly, if we meet the target sync frequency, so I'm using this operand here, then we will re-update the target model using the current model's state dictionary or the parameters. So going over some results, here are some average loss values during training for our agent against a random bot before and after experience replay and the DDQN target network. I'm using a 50 move lookback window to calculate the moving average. And these are the loss values for our base model. And you can see there's a lot of jumps here but it also takes a while for our model to kind of come down and converge. The stagnation of loss values typically means that the model is not really learning as the game goes on, and the x-axis here represents the number of moves or training epochs. This is approximately over 500 games, I believe. And yeah, you can see a lot of instability in the learning here, a lot of jumps because of the lack of experience replay, because our model is just basing its learning off of the very last move that it made. Now here, after we implement DDQN and experience replay, we see a much smoother moving average loss, and we also see a slightly quicker convergence in terms of the loss values over time. So it's able to learn quickly and in a more stable fashion. In addition to experience replay and DDQN, we make a number of other small adjustments to our training setup. So from the previous graph, we saw that the stabilized average loss values after implementing DDQN with replay seems to level off very quickly. When the loss values stagnate like this, there is very little learning that occurs, which renders these future training cycles very wasteful of time and computing resources. In addition, continuing to train under these circumstances does create the opportunity for overfitting to get worse, and the bot could even backtrack on its progress and start unlearning. Overfitting is a situation we generally try to avoid. This is where trained models are not able to generalize their learnings to new instances as a result of contorting their learning way too heavily on the volatility and the patterns in the training data. This happens as a result of a number of things. In our case, it could be because we have training data with a distribution or patterns that don't reflect test data, or it could be a result of training a model for too long. To prevent this, we simply stop our RL bot from training when the loss values during training fails to reach a new minimum after a certain number of steps. So when we reach a new minimum and it doesn't ever get below that, then we can kind of wait a number of periods, and if it still hasn't reached a new minimum, then we'll just stop the training there. The number of steps is defined as our patience level because we exert a certain amount of patience before we cut off training. To address the sporadic nature of our loss values during training, we track a moving average of the last 50 loss values, or the last 50 moves. This modification helps prevent overfitting, unlearning, and inefficiencies from training unnecessary game epochs. We also implement Epsilon Decay. As a refresher, the Epsilon or exploration rate is a rate that we set to tell the agent that a certain percentage of the time we want to take a random move instead of the best move that it thinks based on the Q values. This is because we want to invoke exploration in the RL bot so that it tries to experiment with new strategies rather than it getting stuck in sort of local minima and just self-confirming what it thinks that it knows about the game. We want it to kind of explore the game and massage it and try different things before it starts to settle on a strategy. The exploration rate, Epsilon, is effective in forcing our bot to experiment during the initial training stages. However, as the bot gets deeper into its training process and starts to form cohesive strategies about how to win, we don't really want the bot to continue making random moves 20% of the time, because this could very well interfere with the bot's learning strategies and future moves, and therefore the value estimation updates. Intuitively, once the bot starts garnering a deeper understanding of the task at hand, we want it to start developing its strategies in a non-random way. So we can effectively just decay the exploration rate or just slowly decrease it over time. We set Epsilon rate to a slightly higher value, let's say 0.3, and after every move that we make, we multiply the Epsilon rate with 1 minus some Epsilon decay rate. And this Epsilon decay is a very small value, like 0.0005. For example, if we start with an Epsilon of 0.3, so 30% of the time our bot will make random moves, and a decay of 0.0007, we would have an Epsilon rate of about 7% at the end of 2,000 moves. And this equates to about 133 Connect 4 games, assuming an average game length of 15 moves or so. Lastly, we mask illegal moves. This is just to better handle illegal move generation. We'll mask these illegal moves before selecting the action for our bot. We generate a binary vector of zeros and ones, which tells our agent which columns of the board are available. Then we multiply this vector by the vector of Q value estimates for all actions, and this effectively zeroes out the Q values of the illegal actions before we take the maximum Q value from that vector. So here is our implementation for early stopping, Epsilon decay, and illegal moves. First, we'll do early stopping. So we have some early stopping trackers here. Self.stopTraining is a Boolean flag to tell the main game loop when we should stop training this bot. Min-loss-dict is basically just a tracker for what is the current minimum loss value and how many steps have we stayed in that loss. And then our patience value is set to 200 steps. To implement this, we have an update early stopping method, and we check the last 50 moves. We calculate a current average loss, which is the mean value of the last 50 moves or last 50 loss values in our history. And then if this average loss value is less than the current minimum that we have stored, then we'll refresh that minimum with the current average loss, and then we'll reset our number of steps to 0. Otherwise, if it's not, then we'll just increment the number of steps and get closer to that patience value of 200 before we stop training. If the number of steps we've taken is greater than or equal to the patience, then we'll set our stop training flag to true. And this flag is checked by the main game loop every time we make a move, just to make sure that we are in fact still supposed to be training the model. In the training loop, we'll do our normal get state, get reward, and store experience, and update parameters here. And then at the very end, we'll call the update early stopping method to perform these updates to our loss value checks. In terms of epsilon decay, we specify our epsilon value. We're making a small adjustment here where we set the epsilon value to 0 if we're testing the model, because we don't really want it to make random moves if we're testing. We set our epsilon value to 0.5 to start, and then our epsilon decay is 0.0007. And how that's implemented is every time we make a move in the self.move method, we will grab the move here and then multiply the epsilon rate or update it with 1 minus the epsilon decay rate. And lastly, in terms of the illegal move masking, in the move method, before we make or select our move, we will check the available columns where we take the board array, we'll sum across the columns, and then we'll check to make sure that none of those columns are already full. If our decision is to select a random action, in this case, based on the epsilon rate, then we will select a random choice, but only from the available columns. If we're using our value estimator to determine the maximum Q value to determine our next action, we will take those Q values and then we'll multiply them by the available column vector. And this, again, is a vector of zeros and ones. It'll be 0 if a certain move on the board is illegal or if a certain column is already full. So those zeros will effectively zero out or cancel any Q values for illegal moves. And then we'll take the maximum value of that vector. These are some basic adjustments we've made to our model. To recap, we implemented the memory storage and batch training. We implemented an additional target network for our DDQN architecture. And this resulted in much smoother and quicker convergence in our loss values during training. And we also implemented early stopping based on the loss values, epsilon decay, and we masked illegal moves in our RL bot. In the next episode, we'll get into improvements for our self-play training architecture or our training regiment for the bots. And that way we can start training against much more difficult opponents as opposed to just random move generating bots. Before you go, make sure to leave a like and subscribe if you want to see more of this series. I'm looking forward to tuning the model, having it better perform, and starting to see the kind of strategies that reinforcement learning can learn about the game of Connect 4. But until then, I'll see you in the next one.